yeah. It's the return of the bobblehead. Yes, it is. Looking out of my second story window at home while I'm away here in Wareham, hanging out at my mother-in-law's place. So back again, sun's come out, and it's time to keep playing in Orgoland no matter where you are. You can be in Orgoland on the bus, on the plane, anywhere you want. You can be in Orgoland. All right. Today's class is really all about these amazing epoxide, these three-membered rings with an oxygen in them, and all the wild and crazy chemistry you can do with them, and then a little flashback to the past where we do what's called a dehydration lab, which is, again, a fancy name for some chemistry you already know. So hang on, let's go for a little ride. Woo, scary Mr. Bobblehead. Sorry. Doesn't look anything like me, I don't think. So here are the three reactions, and only three reactions we're going to look at in today's class. So really, it's all about these epoxides over here. Oops. And the wild and crazy chemistry you can see that happens with them is they create alcohols and let you add any kind of nucleophile slash base slash poor nucleophile. So it's still, you're going to see a lot of SN1, SN2 terminology in today's class. And hopefully that is just a review for you. But this is why you can see it's so popular. It's similar to the Grignard in its popularity because you get multiple functional groups added to your molecule and you have control, as you can see, as to where you want to place the alcohol. Which part of the epoxide does the alcohol actually end up on? And it's that control that is really, really cool. So let's go dabble. Ring opening of these cyclic epoxides is what we need to start with. And so then let's get very comfy with what an actual epoxide feels like. So really it is this three-membered cyclic ring, but keep in mind this oxygen, as you can see here, there's red indicating lots of partial negative charge on the top, which means it's sucking electron density from both carbons, making both of these carbons slightly positive. And therefore they're both susceptible to nucleophilic substitution. So this is just going to be a very cool nucleophilic substitution where the leaving group is one of these two bonds. It's going to pop open depending on which carbon the nucleophile attacks at and tries to form a bond with. So very fun. And let's try to make sure that we, keep it in the same vein as nucleophile and electrophilic carbon, and don't make this a whole brand new reaction, because as you remember, the story with Orgoland is just that you find plus loves minus. So break everything down to that, and then let's go play. Two scenarios on how to open it up. As mentioned, you saw there were two rows in the data table from the last slide. So let's go look at scenario number one, which is, I think, the easier of the two to approach because it uses a strong nucleophile. So these negatively charged nucleophiles, strong base as well. So O minus is a very strong base, is also a very strong nucleophile. But in these situations with epoxides, you don't have to worry about elimination because the epoxide itself in the three-membered ring is somewhat stressed out to begin with, and it's ready to burst open. Just give it a molecule that will help open this ring up, and it'll do so. So this epoxide will go through an SN2 reaction, and therefore keep in mind, look here, I have a tertiary and I have a secondary carbon. So you're going to go and label your epoxide carbons, and ideally one will be more or less substituted. If they're equally substituted, then this O minus could react equally with either end of your epoxide. But this is an unsymmetrical epoxide. It's got a tertiary carbon and a secondary carbon. So what does your SN2 intuition tell you? Which carbon would this strong base, strong nucleophile want to react in? In a backside attack? Yes. So notice it wants to come in and react with the less substituted carbon, pushing out and breaking the bond between the C and the O, creating this negatively charged oxygen. Okay, so you've just opened it up. Notice there is stereochemical relevance here because it is a backside attack. That cyclic oxygen and the oxygen side is too bulky for the SN2 to approach, the nucleophile to approach, so it will come from the bottom. Okay, and so it'll come from the bottom and open up the epoxide to make O-, and then all you do is what's called an acid workup, or you just let it sit around because O- is so reactive that it will grab a proton from anything, even the solvent methanol, and what that will do is create more O-. Okay, so that's what you want to do. Try not to worry about these percent yields that are given in the textbook. These are really meaningless statements. Really, they're just trying to brag about how wonderful their reaction was one time out of the 100 times that they did it. So what we want to keep in mind is this is just the major product for this reaction. Okay? Cool. Oh, do you want to be a visitor in my, everybody, this is my mother-in-law.
Hi there. Hi, aren't you lucky to have Mr. Nicholas Doe teaching you? He teaches me an awful lot about what to do around the house.
Oh my gosh. Okay, I'll have to pay her later. Now, my wife said if I put her on camera, she'd kill me. So she's not gonna, you're not gonna get a quick glimpse at her, or you might later, and she might not even know it. But that's my mother-in-law, Bianca. She's awesome. So we're just, she might want to learn about ring opening of epoxides too. So here we go. A little diversion there. So keep this in mind and notice the position of the new group and the alcohol are anti to each other, and that's due to that backside attack. So stereochemistry plays a role here. Here's kind of a summary of it all. Again, if you spy basic conditions, you put these two together, basic conditions, then it's going to do a definite SN2 reaction and attack the less hindered carbon of the epoxide. Doing so will cause inversion, and you'll only see that inversion if you end up with a chiral carbon. So chiral carbons are going to be visible, but if you're attacking, it's not a chiral carbon, it's a CH2 on one end of the epoxide, you can't ever even tell it was an inversion. All right? All right. Now, scenario 2. If I can do a basic attack on the epoxide, this is what happens if you add acid first. Very, very important. Notice the reagents here, there is no strong nucleophile. So in the same process that you figured out SN1 and SN2, and it's SN2 if you see a really good nucleophile or a strong base, it's E2, then here this is going to be SN1. Oh, that was my brother-in-law. You saw him walk by. Say hi, Mike.
Hi, Mike.
There you go. See, there goes Jaime.
Happy 4th of July.
Yeah, there we go. All right. So in this situation, you don't have a nucleophile to do a backside attack, but you have this partially negative oxygen. Ooh, are we all right? Okay. So this partially negative oxygen is going to grab this source of protons. It could be sulfuric acid. So look out for H2SO4, but some non-basic, non-strong nucleophile, acidic, weak nucleophile species like this methanol is going to start this process, and therefore you protonate the oxygen first. Very similar to how you protonate an OH group to make it a better leaving group. You protonate the epoxide to make it a better leaving group. And notice when you protonate the epoxide, we have, again, a tertiary carbon here and the secondary carbon here. So as that oxygen gets protonated and feels very positive, you're going to have a positive charged oxygen at this point. It is really sucking electron density from the bonds of the epoxide carbons. And the ones it can suck the most electron density from is the more substituted carbon. right? This is a much happier tertiary carbocation if I were to form one. So it's SN1-like, but not completely SN1 because that bond's not broken yet. But to understand where is the nucleophile going to add, it's really important that you spy this neutral methanol as a possible poor nucleophile in an SN1-like reaction is now going to be more attracted to this tertiary carbon, even though it's still going to do a backside attack on it. Really cool. It's still stereochemical. So I don't lose all my stereochemistry, but I use the idea of SN1 chemistry. So it will now do a backside attack, breaking this bond completely, giving it to the oxygen. And then you can see the hydrogen at the very end falls off as H+. All right. And you end up creating this ether alcohol. But notice the alcohol is now on the less substituted carbon, and the nucleophile is on the more substituted carbon. So when you see this product, if you see a new nucleophile and an alcohol, and you see it in this fashion, then you can understand it must have come from a weak nucleophile reaction. This was not previous to this was not OCH3 minus, because that nucleophile would have attacked the less substituted carbon. So this is not what was used to make this product. It had to be its conjugate acid, its weak nucleophile. Very powerful tool. All right. Summary of it all. It still follows SN1 regiochemistry, meaning wants to attack the space of the tertiary carbon or the more substituted carbon, but it uses SN2 stereochemistry because it is still a backside attack, because that oxygen's at the top filling up the entire top of the epoxide. So the attack can only come from the bottom. All right, very, very cool. All right, any questions about that? Cool, bring them to study group this week. Email your questions to me, send them to me somehow. Don't let this slide. This section on epoxides is really powerful. And again, like Grignard, it's a way of, making carbon-carbon bonds. I could throw a Grignard at this epoxide, make a new carbon-carbon bond, open it up and make an alcohol, which could then take me to the next step and the next step and the next step. So it is a very powerful tool in making different functional groups on your molecules. All right, pause for a second, see if you can figure out the products of these two reactions, and then I'll show you the answers. Cool. Were you spacing out, looking at the beautiful ocean view? I understand. I would like, yeah, it's kind of cool. I like to do that too. Hopefully though, you came at this problem and approached it and noticed the epoxide has stereochemistry to it. That epoxide's wedge sticking out at you. So all the new reactions that happen to it have to come from the backside and should be dotted lines. Hopefully you spied KOH in water and solvent, really inconsequential, is going to fall apart into OH minus. So all of these reagents are just there to make a very strong base, and therefore you're doing a basic opening, an SN2 opening, an SN2 stereochem, regiochem, everything chem of this epoxide. And at the end, it'll just grab an H off of the water and become your 2. So this OH minus is going to want to attack the less substituted carbon, the blue highlighted one, and open up the ring. Okay, breaking it open this way. So notice this is the green oxygen versus the pinko. Cool. How'd you do on the acid side? All of this is just to communicate that you have H plus and you have a very poor nucleophile in H2O. Okay, no OH minus. Did you come up with this? Stereochemical answer. Granted, the products are built exactly the same. They're both diols and they both have oxygen, OHs at the same carbon, but play around. Here you have chiral carbons. I should ask you, are these enantiomers, diastereomers, meso? What's the relationship between these two? And therefore you have stereochemical control over which one of these two products you would want to make. So keep in mind, if I were to give you this product and this starting material, you would be able to tell me which reaction, acidic or basic, would get you to this product. Okay, that's your control. Cool. Let's see if you can do this one for class. Please come with actually the mechanism of your reaction to show why you picked one of these compounds or compound or compounds. Notice E is A and D. So look, a lot of stereochemistry here. Whenever I get a lot of stereochemistry, R and S should come to your rescue. Feel free to use R and S to support your answer. Okay? All right. This is it. Epoxides, we're all done. Let's take a little brief look into something you've seen before. Another musical interlude.
Astounding. Time is fleeting. Madness.
Depends on if you've
Takes its
seen
toll.
this before. This came
But
from a
listen
movie.
closely.
Not for very much longer.
Do you recognize this?
I've got to keep control.
Classic.
Doing the time war.
Flash to the past. Blast from the past. If you have not seen Rocky Horror Picture Show, it is definitely something you got to experience at least once in your life. Put it on your bucket list. Little on.
With your hands on your hips.
All right. This is the dehydration lab. It is just a fancy E1 reaction. Let me show you the whole thing and we'll talk about it. Okay, so, sorry, Time Warp gets me into Rocky Horror Picture Show. That is a great movie. This dehydration of secondary and tertiary alcohols, notice it has to be SN1, is a process because, notice here, there is no strong nucleophile. There's just water. And really, water is so incredibly poor that once you protonate the OH to make it a good leaving group, it will fall off and form the carbocation. So the first step is going to end up with this carbocation. This carbocation here at that carbon. And now I have all these beta hydrogens that are ready to just fall in, and it could be either side. In mine, I showed this one falls in and we lose H+. This is a much faster reaction than having this carbocation bump into a water molecule. So instead of SN1, I could do that, but notice I've also given you heat as a way to tell you, please make the elimination product here by E1. So it could go SN1, I could have some minor product that would be the alcohol again, right? If this acts as the nucleophile, then all I would do if this spits in here is I would go right back to my starting material. So basically you see no difference. So no SN1 here because it's the same as the starting material. So the only product you would ever see in an acid water reaction with alcohol is an alkene. And therefore we're dehydrating it, taking water off. And so just be on the lookout that sometimes I might give you this reaction as HCl. That's also a strong acid and can protonate the OH to make it a good leaving group. But now I've also given you a good nucleophile. And I've also decided, oh, don't heat it. What would HCl do in an SN1 reaction at 25 degrees? And you're right, it would make the chlorinated product. So this is all old news. Feel comfy, feel a little easier. That's because it's more familiar to you. All the language here is. But keep it in this idea of ways of making alkyl halides from alcohols, because all these previous reactions we've shown you, from Grignard, carbon-carbon bond forming, to Grignard, to epoxides, are all making alcohols So this is why this alcohol reaction is stuck in this chapter, because now I can take these alcohols and make alkenes, which can go off and do amazing things that we're going to see in a few days. Okay? All right. Let's practice. Can't get better at Orgoland without practice. So please come to class with the answers to these questions already pre-written, ready to go. Or please feel free to comment on people's answers to these questions. Okay? Can't leave without Mr. Bobblehead. Okay. Have a great day. See you soon. Bye.